All right. Thank you all for braving the elements to be here. Um, so one thing I've been asked to advertise to you, I think this is relatively new. I don't remember having this before, but the NSM student leadership has study nights for a lot of the core courses. So ours is coming up Thursday evening in this room. So if you want a chance to review the material and get some help and feedback on how you're doing, that's a great opportunity for you. The other thing I want to point out before we start today's material is that the lecture that I missed on Thursday, that should be the only time I missed this whole semester. That material is fairly important, so make sure you're up to speed on it. So it was all about Lewis structures. I don't know if Professor Larson reviewed any of that or not, but the notes in the recording have all that information. And I say it's an important topic not because it's going to be covered any more heavily on exam one than anything else will, but to really understand the stuff we're doing in chapter 4 and to be able to apply that material, which we're going to start today, you have to be able to draw a good Lewis structure. So Lewis structure is one of those topics that just doesn't go away as soon as you learn it. It's going to carry us through most of chapter 4. That should be about it for this course, but then for those of you that want to take organic chemistry in the future, or maybe don't want to, but you have to, Lewis structures is critically important for all of organic chemistry, both 1 and 2. So you have to make sure you're clear on how to do all that. Okay, but the topic today that we're going to start with, which is going to close out chapter 3, it's going to close out the material for the first exam, which starts in a little bit less than a week. The first topic is going to be nomenclature. So we've talked about ionic bonding, covalent bonding, and how atoms can combine to form compounds in those ways. And today we're going to learn how to name them. So we've talked a bit about the formulas of especially ionic compounds already. Today we're going to discuss the naming conventions that we use for a few different classes of those compounds. And then we will also likely be able to start chapter 4 as well, which is not going to be until the second exam. Also, per tradition that I'll try to keep up most of the semester, a little bit of reminders and insights into study habits and things to keep you on track. So obviously with the exam coming up, this might be a common question you have. How do I know if I'm prepared for the exam? I think the absolute best thing you can do, and I've been trying to emphasize this throughout the semester, but definitely during the next week as you get ready, you just need to do as many practice problems as possible. And to make sure you're prepared for the exams, they should be done without your notes in front of you. You're not going to have your notes on the exam. It's easy to convince yourself that you understand something by just sort of working through it with your notes in front of you. Oh yeah, I got that. But you really have to test yourself to actually know if you're on top of everything. It's not so much in this first exam that you'll see this, but a lot of the problems that we'll have in the later parts of the course are multiple steps, and you have to get every single step right to get the question right. So again, you might think that you're on track to something, but if you're missing one little thing. So that's where doing practice problems without notes is critical. We have the homework assignments reopen up as practice that you can access as many times as you want. I have an exam review that's posted in Canvas, which I emailed you about yesterday. So there's a section in Canvas with exam review materials. We're not in Blackboard anymore, sorry. In Canvas, we have a practice exam as well. That's going to be linked to WebAssign. Almost should be identical in format and length to the real exam. I would recommend doing that towards the end to really see if you have any remaining gaps that you have to fill towards the end of your studying. I certainly encourage you to study in groups. It's good to make friends with people in your classes, and I've had a lot of those types of things start in my courses. So group studying is great, but again, making sure you still do a lot of individual practice. Don't sacrifice that. And I've been trying to give you recommendations all semester on what to do. So if you've been following those, and you're convinced that you've been learning the material every single week and putting good effort into the homework, you should be in pretty good shape for this exam. So that's a little bit of reminders about that. All right, so finally into the course material for today. So I don't think these table numbers have changed, but there are a series of tables in chapter 3 that are centered around nomenclature. So different things about the rules we're going to cover today, some of the names of parts of compounds that we'll get into where I can't cover them in ad nauseum, but so you want to make sure you refer to those as you're practicing this material and learning it. I'll try to give you all the essential information today, but you certainly will want to refer to that part of your book. And I have those tables reproduced in the notes if for some reason you don't have the book or you're confused about which ones to look at. All right, so the first thing we're going to start with are ionic compounds. And really the first category that we're going to discuss in detail are called binary ionic compounds. So binary ionic compounds, as the name binary implies, is just going to be an ionic compound that has two elements in it. And as we've been talking about ionic bonding and the formation of ions throughout the last few weeks of this course, we should recognize that that involves a metal with a nonmetal. So the metal loses electrons to form a cation. If it's in the first two columns of the periodic table, we can easily predict what charge that would be. And then the nonmetal that it pairs with is going to be something towards the right of the periodic table, which again, knowing where it is in the periodic table, we can predict if it's going to likely be -1, -2, or -3 in its charge. Okay? Binary ionic compounds are very similar to are very simple to name, and there's not a whole lot to it. So you just name the metal first. Whatever the metal is in the compound is named first. That's going to be, again, the part of the ionic compound that would represent the cation. And then you're going to put the nonmetal second. Now, as we'll talk about in a little bit, there's a little bit of a modification you'll have on the nonmetal part of the name, but that's the order that they go in. And that's nonmetal is going to be the one that would be the anion in the ionic compound. And this ordering convention, metal first, nonmetal second, that applies to both the formula and the name. So if you're writing the formula for an ionic compound, you should put the metal first and the nonmetal second. Or when we're naming them, as we're talking about today, that's the name, that's the order they come in as well. All right. So then for the cation, the metal part of the formula, that you just take the name of the metal. We will talk about one modification you sometimes have to do with transition metals. But for main group metals in the first two columns, the first part of the name is just the name of the metal. Sodium, lithium, potassium, whatever the case is. So if you're, again, if you have Na plus in your formula, the first part of your name is just sodium, no modification to that. If you have calcium 2 plus in the formula, you just put calcium at the beginning of the name. So you don't modify the name of the metal at all. The anion is the one that does get modified a little bit. So you're going to use the root name of the element, but you're going to change the ending to IDE. So if we had an ionic compound that had F minus in it, F is the element fluorine, but we wouldn't put it in the name of the compound as fluorine, we would put it in as fluoride. So it would become fluoride with an IDE ending. Or similarly, O2 minus comes from oxygen. We don't call it oxygenide, we just call it oxide. So but again, the IDE ending tells us that it's the anion part of the formula. And similarly, N3 minus, another common one, would become nitride. Now, one key thing about naming ionic compounds that's going to be different than what we do with covalent compounds later on is that there's going to be no prefixes in the names. So we don't have prefixes telling us how many of each ion there are. And the reason we don't need that is because the reason we don't need those for ionic compounds is because the charges of the ions are going to tell us how many of each ion there should be. We already talked about how to predict the formula for an ionic compound. So if you know which ions are in the compound and you can use the periodic table to predict their charges, that'll give you the ratio. You don't need extra information in the name to tell you what that ratio would be. So when we're writing the formulas then, as we already talked about, you need the lowest whole number ratios, and that comes from balancing the charges of the cations and the anions. But the number of each that you have in the formula does not show up anywhere in the name. The name is just cation plus anion with an IDE ending for the anion. All right, so we already talked about how to do the subscripts in the formula. For the name, though, those subscripts don't get translated into the name at all. You just name the cation and the anion, and where it is in the periodic table will normally tell you what the charges are, and that allows you to easily predict the formula from that. So with some simple main group ionic compounds, let's go through some examples. So if we have MgCl2, now one thing that it's in the syllabus, but that doesn't mean you actually read it. So you are responsible for knowing the names and symbols of the first 36 elements, not what order they come in or anything else about them. But if I give you the formula MgCl2, you should know that Mg is magnesium. not manganese or anything like that. So make sure you can match up names and symbols. The periodic table that would give you on the exam, as you've seen, if you've looked at the homework assignments, does not have names in it, just has symbols. You have to know which name goes with which symbol for the first 36 elements. Now, you might think that's a dumb exercise, but we're trying to get you to speak the language of chemistry. So you need to learn some of that stuff to be proficient. Okay, so for MgCl2, it doesn't really matter what the charges are, but we would have Mg2 plus and 2 Cl minuses. That would be the individual charges. But again, none of that really matters for the names. We just put the metal first, which is magnesium. And then the nonmetal, which is chlorine, we change the ending to IDE, so it becomes magnesium chloride. And we don't need anything in the name to tell us that there's 2 chlorides in there. We just say magnesium chloride because magnesium would always have a +2 charge, which means in order to form an ionic compound, it would have to have 2 chlorides. There's no other way about it. Okay? So we just call it magnesium chloride. This one here I probably shouldn't have given you because the cation CS is beyond atomic number 36. So you wouldn't have to know the name of this off the top of your head, but if it was multiple choice, we would just give you all the answer choices that make that obvious. So CS is cesium, so that's going to be the start of the name. Again, that's not one you'd have to necessarily know because it's too far down the periodic table, so apologies for that. But this one you should know, oxygen O. But as an anion, as we just said, this becomes oxide. So cesium oxide would be the name of this. Again, nothing needed to tell us that there's 2 cesiums and 1 oxygen, just cesium oxide, because those ones have very predictable charges. Another way then that we could ask these types of questions, and we give you the formula, you give us the name, or a slight variation on that is we don't tell you the exact formula. We give you the 2 elements that are involved and ask you to predict the formula and or the name of the ionic compound that would form. So that requires us to go to the periodic table. Again, I gave you a bad example here because this one's too far down. So strontium is Sr. That would be given to you in the problem for this case because it's too far down the periodic table for you to have to memorize. But strontium is Sr. And same with iodine. It's a terrible example. But if once we know the symbols for those, which again, that's not one you have to necessarily memorize. So they're past atomic number 36. But once you have the symbols, the 2 parts of this question, formula and the name. So then what we're going to do in either order is we're going to go to the periodic table first to figure out the charges of the ions. That's required for the formula. So if we go to the periodic table, all right. So again, these are past 36, so I shouldn't have given them to you in this format. But Sr is here, number 38. It's in the second column, so we would predict that it forms 2+ cations. It would lose 2 electrons to get to the krypton Kr configuration. Iodine is the heaviest non-radioactive halogen, so it's here in group 7. Second to last column will gain 1 electron to get to noble gas configuration, so it would be I-. Okay, so those are the charges of the ions involved. That's important for getting the formula, not so much for the name. So when we want to get the formula of this, it's going to be strontium 2+. This is sort of a review of things we already covered. I-, the sort of approach that doesn't require a lot of thought, is just to take the charges and make them subscripts. And so you get this -1 becomes a subscript of 1 on strontium. The 2 becomes a subscript of 2 on iodine. So SRI2 is the formula. But again, we don't need the name. We don't necessarily need the formula to construct the name because it's just going to be the name of the metal plus the name of the nonmetal with an IDE ending. So that would just be the name. So formula, name. You don't even need to really know the formula to get the name in this case. For sodium and sulfur, these ones we should be able to do off the top of our head relatively easy, at least get the symbols correct. So sodium is Na, sulfur is S, so we need to locate those on the periodic table. We've seen sodium quite a bit already. It's one of the alkali metals. It's in group 1, so that means it was going to form, we would predict it forms a +1 cation, losing 1 electron to get to the neon configuration, so that's going to be sodium +1. Sulfur is number 16 here. Second to last column right under oxygen, so it would tend to gain 2 electrons to get to a 2- anion to achieve noble gas configuration. So it's going to be Na+, S2-. That gives us the formula Na2S. The name, we don't really care that there's 2 sodiums in there. We just call it sodium sulfide. So again, S is sulfur, name at the end becomes IDE when it's in an ionic compound. All right, so that's how it works for binary ionic compounds. There's not a lot of variation on that theme. The one place where things change a little bit is when you have ionic compounds that involve transition metals. Those are the ones that are in the middle part of the periodic table that we've talked about a bit. There's also a few other main group metals where this applies. So indium, thallium, tin, and lead. Further down, so not ones you're going to likely see as much. But the key distinction between with these types of metals, the transition metals plus these four, is that there are two different stable cations, or sometimes more than two different stable cations that they can form. So unlike group 1, which always forms +1 cations, unlike group 2, which always forms +2, the metals that are in the middle part of the periodic table often have more than one possible cation they can form. And so that means if we just name the metal and the nonmetal together like we do for binary compounds, we're not really going to exactly be able to translate that to a formula because we don't easily know the charge on the metal. For example, iron is very commonly iron +2 or iron +3. There's some other charges it can adopt as well in some situations. So we can't just say iron oxide and know exactly how many irons and how many oxygens are in the formula. We need to have something else there. So the rules are still very similar. We don't change things a whole lot. The formula is exactly the same. We put metal first, non-metal second, lowest whole number ratio. So we just put cation first and anion in the correct ratio to balance the charges. The difference comes into play with the names of compounds that involve transition metals. All right. So in this case, what we use is a Roman numeral in parentheses to indicate the charge on the metal. Because in this case, the charge on the metal could be a few different things, more than one different thing. So we have to indicate that in the name. We put in Roman numeral in parentheses after the metal name to denote its charge. So if we have, as we said, iron can have two different common charges, really more than two, but the two most common are iron 3 plus, iron 2 plus. There's no way from the periodic table to easily predict that, so there's not really a prediction to be made there, but those are the two that we often see with iron. So if the ionic compound has iron 3 plus in it, the name of that compound would include iron at the beginning, but with a Roman numeral 3 afterwards to indicate that iron has a charge of +3. Same story with iron 2 plus, the name would have iron with a Roman numeral 2 after it. All right. Now, one other thing I want to point out, you're not going to get tested on this, but just for your benefit as you go through your chemistry education, and you might see this from time to time, so I don't want you to be confused by it either. There's also another naming convention for transition metal ionic compounds that changes the ending of the metal name instead of putting a Roman numeral after it. Again, that's not one we're going to hold you responsible for, but you might see it out there, so I want to make sure you're not totally lost if you do see that somewhere. So if you have a transition metal that has two possible charges like iron, for example, the one with the higher charge is going to get an IC suffix in the metal name. And it often typically uses the Latin root. So a lot of the symbols for the metals, so why is iron Fe? It's because the Latin name for iron is ferrum. So what you do for iron 3 plus then, in the common naming situation, is change that to ferric. So if you see something that's like ferric sulfate or ferric chloride, that indicates that the iron in that compound has a +3 charge. That's an old convention. We don't use it as much anymore, but in case you see it, for example, maybe in the lab or in reagents that you might use in biology sometimes have these names. And then for the lower one, the one that has the smaller charge would be OUS. So in the continuing example of iron, the other common charge for iron is 2 plus, which is a lower charge than 3 plus. So that one gets the OUS ending. All right, so now you can identify up here in the top right what is an inorganic chemist's favorite carnival ride. It's the Ferris wheel. All right, so that should hopefully make sense to us now. But again, that naming convention is not one we're going to really test you on, but I wanted to make sure you were at least exposed to it. But that's how it is for transition metals. The most common thing we'll see in these is you're going to need a Roman numeral in parentheses to indicate the charge. Okay. So we'll get some examples of transition metals in a little bit. But the first thing I want to cover before we get to that are a thing called polyatomic ions. Again, I hope the table number is correct. I forgot to check if I don't think our book changed since the last time I taught this, but anyway, there is a table in the book somewhere, and it's reproduced here, possibly numbered differently, but otherwise identical, that lists what are called polyatomic ions that you need to know. Now, what is a polyatomic ion? It's a group of nonmetals typically. Sometimes it has a metal at the center, but it's a group of atoms that are bonded together covalently, but overall they have a charge. So unlike a molecule, which is totally uncharged, it's a group of covalently bonded atoms where there is a net positive or negative charge. Negative being the ones that are most common that we'll see in this course. So that's what a polyatomic ion is. It's groups of covalently bonded atoms. Now, this is sometimes a frustrating topic for students at this part of the course because you're getting towards the end of your first exam material and it's like all of a sudden, oh no, I have a bunch of things to memorize. Now, I don't like to use the word memorize. I like to use the word learn. For example, when you were a toddler and you were learning how to speak, did you memorize how to speak or did you learn how to speak? You learned, right? So it's something you have to kind of pick up gradually, and it is important just to have that. There is a little bit of try to recognize patterns with this too. So when you look at the table, which is I'll show you later on briefly, but the table looks like it has a ton of things in it. I'm like, oh my gosh, I had to memorize all these, but there is a little bit of a pattern involved. So many of the polyatomic ions that we have are, as you'll see, what are called oxoanions. They're some center atom with a bunch of oxygen around it. And in that case, very often you're going to have the possibility of having different numbers of oxygen atoms around the center atom. And typically, the smallest number of oxygen atoms is going to have the ITE ending. And then if you have more oxygen atoms around the center atom, it'll be ATE. So I'll point out a couple of those when we look at the table. But try to recognize patterns, and it ends up not being so bad as thinking that, oh, I have to memorize 20 things with no rhyme or reason. There is a little bit of a pattern to it for some of them at least. All right, but when you're putting polyatomic ions into the formula of an ionic compound, if there's more than one of those ions in the formula, so just like we can have more than one chloride or more than one sodium ion in a formula, as we saw already today, if there's more than one polyatomic in the formula, it needs to be enclosed in parentheses. So if there's more than one in the formula, parentheses are used to enclose the entire ion. I guess it wouldn't be wrong to have it in parentheses even if there's only one, but it's just not conventionally done. And then the subscript that indicates how many of those ions there are is going to be on the outside of the parentheses. Yeah, this is only in the formula. We don't put parentheses in the names, just in the formula to indicate that if there's more than one of those ions in the formula, that's how we do it. So a very simple example would be if we have sodium, which we already said is a +1 cation, the anion NO3- is called nitrate. That's one that you have to learn. And that also has a 1- charge. So if we're combining these two ions to form a compound, just a sodium cation with this polyatomic anion nitrate, NO3-, that whole group of 4 atoms, nitrogen with 3 oxygens around it, has a -1 charge associated with it. We still just have to balance the charges. So you just need one of each. So those would form a compound NaNO3. NaNO3, correct. So there's just one of each ion in the formula. And because there's only one nitrate, you don't have to put it in parentheses. In my opinion, it wouldn't be wrong to do that. So I would just get in the habit of not doing it that way because Canvas is or Web of Science pretty picky about how you format things. So I would say leave it out. Absolutely, yeah. Okay, so then what we have is if we were to make a compound that had same anion nitrate, but this time with calcium 2+ and still NO3-. So remember, we don't change the charge on the polyatomic anion to try to balance anything. NO3- is always nitrate, always a 1- charge. You don't want to just magically put another charge in there and be like, okay, one of each, we're done. It's just 2 minus this time. Keep it always the same charge. The charge is fixed on that anion. But now we have to use subscripts to balance out the charges. So this 1 becomes a subscript on calcium. The 2 becomes a subscript that applies to the whole nitrate anion. So you need to have 2 of these NO3 minuses to balance the charge. The way that we indicate that is put the whole thing in parentheses, NO3, and then the 2 on the outside to tell us that we have 2 of those NO3 minus anions in the formula. All right, so we don't do this. We don't do, this would be confusing, right? To put NO3 and then just a 2 without parentheses, because then it looks like NO32. And we don't combine them either. We don't go N2O6. We would lose that information about the nitrate actually being there. So we wouldn't write it like this either. So both of those would be incorrect. We want to write it with the anion in parentheses, indicating that it is nitrate NO3 minus, but there's 2 of them to balance the charge. So you'll get used to that, but it's just a slight complication that we have. All right. So let's just do a few examples now that involve transition metals and or polyatomic ions to just wrap up this part on ionic compounds. All right, so if we have Fe2O3, all right, so again, Fe is a transition metal. If we find it in the periodic table, it's right here. So it's in the middle of the transition metal series. So we don't have an easy way of predicting what the charge on that would be. It's not one of these first 2 columns here. There's a lot of variability. As you said, +2 and +3 is most common, but there could be others as well. Okay, so then if we want to get the correct name for this one, we have to figure out what the charge is on the metal. So that actually, in this case, requires us to work backwards from the formula. So when you have ionic compounds that involve transition metals, you don't change the formula, the charge of the anion. The charge of the anion is still whatever it would be from the periodic table, or if it's a polyatomic anion. And so what we would have then is, in this formula, we have 3 oxygens. Those are still going to be 2 minus charge, okay? So we don't have any difference in the charge on oxygen. It's still in the same part of the periodic table. It's still predicted to be 2 minus, but the iron is one that we have to figure out. So we have, all right, so we have, for real, this time is he gone? All right, so we have 3 oxygens with a 2 minus charge. I'm sure there's a good reason for that. It shouldn't make fun. All right, so we have 6 minus charge. We have 6 minus charges on the anions, 3 oxygens that are 2 minus each. So then we need to balance that with the cations, which is variable in this case. But if we have 2 cations, each of those needs to be 3 plus to balance the charge. So in this case, with transition metals, if you're given the formula, you have to work a little bit backwards to get the charge of the metal. We know the charge from the anions, that we can easily predict from the periodic table or from whatever polyatomic it is, if that's the case. And then we go backwards from there to figure out that we need a 3 plus on the metal. So now that's +6, that's -6, so they balance out. So then when we're naming this compound, it's going to start with iron, but because it's a transition metal, we need the Roman numerals to indicate the charge. So iron 3 would be the correct way to start the name. We don't do anything to the anion, it just stays as oxide. Okay, so that's the only slight difference. You need the parentheses to indicate the charge when there's a transition metal. And then same story here with CuSO4. Again, I put it in parentheses, which is not wrong. Often it's not in parentheses, so it could be also just written as CuSO4. Both of those would, in my mind, be correct. Hopefully in WebAssign's mind as well, or I'll have to do a lot of regrading for you guys after I told you that. But anyway, that's the formula of that compound. And so what we can do is, again, we have to sort of work backwards to get the charge on the metal. So we have to recognize, once we learn all the polyatomic ions, that SO4 carries a 2 minus charge as the sulfate anion. Again, if you don't know that yet, there's time to get it down, but that's the sulfate anion. And then our copper is the one that has variable charge. Copper is also in the transition metals. It's towards the end, number 29 there, but it's still a transition metal, so its charge is not easily predictable from its location in the periodic table. But if we have a 2 minus anion and 1 cation to balance it, the cation will then have to be 2 plus to make sure that the charges cancel. So that gives us then the name that starts with Cu is copper, 2 in parentheses to indicate that it's a +2 charge, and then the name of the anion unmodified, just sulfate. All right, so copper 2 sulfate. Again, the older naming system that you're not responsible for, what might call that cuprous sulfate. So OUS, sorry, cupric in this case for copper 2, cupric sulfate with the higher charge for copper being the IC ending. But again, don't worry too much about that. All right, and then a couple that are slightly more complicated, giving the formula from the name. This one is actually, with transition metals, fairly easy to do because the charge for the transition metal is directly given to you. So there's nothing you have to do to figure that out. You just have to know the charge of the anion, either from the periodic table, if it's just a single anion, or if it's a polyatomic, you have to just know the charge. There's not a systematic way to do that necessarily, at least at this level of chemistry. So for chromium 3 permanganate, we write the names of the ions out. So the 3 tells us that it's chromium 3 plus Cr. You have to know the symbol, of course. And then permanganate, this is one of our weirder polyatomic anions, but it has a metal at the center, manganese, which is Mn, 4 oxygens, and a -1 charge. And that one's probably the hardest to rationalize for us, but you just have to know it. All right, so we have those 2 ions, and then same story as we did before. Once we know the charge of the ions, we just have to cross over the subscripts to make them balance out. And so what we get is 1 chromium, 3 permanganate. So we put that in parentheses to indicate that there's 3 of them. So 3- from the anion, 3+ from the metal, the cation, and they all balance out. And then last one, tin 4 chloride. This one should be getting familiar by now, but chloride is from chlorine, which is here. And then it's going to gain 1 electron to make a -1 charge. And so what we get is Cl- for chloride. Tin is we're told here, sorry, the symbol for tin is Sn. That's another weird one. I'll give you some weird ones here just to clue you in on some of the strange ones. So tin 4, we'll put the 4+ up there as the charge now. And then we just have to cross over to balance everything. So it's going to be 1 tin, 4 chlorides to balance the 4+ charge. And so SnCl4. So in some ways, working backwards from the name to the formula might be slightly easier, but that depends on your perspective. So that covers ionic compounds. Any questions on those before we move on to covalent? Yeah. You have to sort of learn them. So there's a table later on. I put it towards the end, but so they have, I mean, these ones you don't really have to, these are the monatomic ones. These ones you don't really have to memorize because they come from the periodic table. But and then these are the transition metals, which again, we don't really want you to necessarily memorize all of those. But the important ones are these ones here. So there's this table here, a little bit small on the screen, but you'll have it either in the book or in the notes to look at. And again, some patterns that show up. So NO2- and NO3-, 2 anions that have nitrogen and oxygen. The one that has fewer oxygens has the ITE ending, nitrite. The one that has more oxygens has the ATE ending. For you guys remembering the charges, there's not going to be really an easy way to rationalize that. If you had a little bit further advancement in chemistry, and once you get like really towards the end of this course, you might start to pick up on the reasons why, you know, nitrite is NO3- with a 1- charge versus sulfate SO4 2- with a 2- charge. There's like some way to rationalize that if you have a bit more advanced of a chemistry background than we get in this course. So for you guys, the charges are going to just have to really be memorization. There's no way around it, even though I hate that word. But that table has all the ones that we expect you to know. As you do the homework questions and especially the quiz questions, you'll kind of get an idea of which ones are most common, which ones we see the most. They're not all going to be showing up equally, I would say. Some are more common than others, just in general in chemistry. So you'll get the hang of it as you practice it more. Any other questions? Okay, so then as we move to covalent compounds, in a lot of ways these are easier. So for these, you do need prefixes to indicate how many are in the formula, because for covalent compounds, it's not about balancing charges like it is for ionic compounds. You're going to just have some number of nonmetal atoms combining to make a compound, and very often they can combine in different ratios. So you need prefixes on the name and to indicate how many are in the formula. So the one that we've already seen in this course a long time ago is carbon and oxygen form 2 very common compounds. Carbon monoxide, which is CO, carbon dioxide, which is CO2. So different numbers of carbon and oxygen in the formula, different ratios. So the name has to reflect that in this case, because there's no way from the periodic table to easily rationalize that. So the way we do that for covalent compounds is we use prefixes to indicate how many of each element there are in the formula. These are for binary covalent compounds, really the major type that you'll be responsible for. Binary, again, meaning a compound that just has two elements in it and no more than two. Okay. So the prefixes are fairly common. They come from probably, I think, Latin in this case. So mono for one, di for two, tri for three, tetra for four, penta for five, hexa for six, hepta for seven, octa, nona, and deca. We don't see numbers that big very often, but they can show up. So those are the prefixes, and typically then what you'll see in the name of a binary ionic or binary covalent compound is that each element will have a prefix in front of you telling it how much there is. The only time you leave the prefix off is the mono only shows up if it's on the second element in the formula. So if the first element in the formula only has one of them in the formula, you don't put the mono in front of that. That's, again, just some weird convention. So that's why for CO is carbon monoxide, not monocarbon monoxide. And CO2 is carbon dioxide, not monocarbon dioxide. We leave the mono off if it's the first element in the formula. There's only one of them. The other thing that you'll sometimes see for some of these, for these ones at the end here, the 4 through 10 that end in A's, a lot of times, if the atom name starts with a vowel, the A will be left off. So you would more commonly see tetroxide than tetraoxide. Get the hang of it from the homework. I don't think that's something we're going to really hold you to necessarily, but as you see them and start, you'll notice that that's commonly the case when your atom name has a vowel in it at the beginning. All right, so with binary covalent compounds, that's the type we're going to really be focusing on. That's where these prefixes come into play. It's a covalent compound that only has two different elements in it. So no more than two, exactly two elements in the formula. Defines it as a binary covalent compound. And so the rules for nomenclature on these is that it's not always as obvious what order they come in, but there is a convention for it. So we don't have metal and non-metal here, so we don't put metal first, non-metal second. Covalent compounds are just collections of non-metals together. And so the first element in the formula in the name is that with the lower group number, the one that's further to the left in the periodic table. So that's why when we say carbon monoxide, carbon is in group 4, oxygen is in group 6. Carbon's to the left of oxygen, so the element that's to the left gets named first. So that's why it's carbon monoxide and not oxygen monocarbide. Okay, so that's the order that they come in, is left to right on the periodic table. If they're in the same group, so if they're in the same column of the periodic table, then the one with the larger, the one with the lower row number, the higher period number becomes first. So the higher period, that'd be the one that's lower down in the periodic table, the one that's heavier, if you want to think about it that way. So if you had iodine and chlorine combining to make a covalent compound, so I down here, Cl up here, iodine would come first in the name of the formula because it has the higher period number. It's further down the periodic table. Okay, so that's the convention for the ordering of them. And we still use, for the name, we still use the IDE ending on the second element. So even though it's not ionic compound, that part of the naming convention still holds. The second element will end with IDE in these binary compounds. All right. And again, the key difference between covalent an ionic formula is that covalent compounds do use prefixes in the name, those that we just listed on the previous slide. So these are collections of nonmetals. So you don't have the situation of predicting which one's positively charged and negatively charged. It doesn't work that way anymore. We're sharing electrons. We're not forming ions here. So you need prefixes to indicate how many of each there are. And the other important distinction is that we don't reduce the formula to the lowest whole number ratio. So as an example, NO2 and N2O4 are two different compounds. So we don't want to reduce the formula of N2O4 to NO2 because that makes it a totally different compound. Okay, so we for covalent compounds, those that involve combinations of nonmetals, it is possible and sometimes common to have a formula that's not in the lowest whole number ratio. Maybe a more common example than N2O4 would be hydrogen peroxide, which is H2O2, covalent binary compound, and we don't reduce the formula to HO. We just say H2O2, even though that's not the smallest ratio, because that gives us information about how many of each atoms are in one molecule of the compound, which may not necessarily be the smallest whole number ratio that's possible for that compound. All right, so let's do a few examples of these. This is, I think, a little bit easier even than ionic compounds because you just need to know the prefixes. You don't need to know anything about predicting charges or anything like that, or memorize a bunch of polyatomic ions like we do for ionic compounds. You just have to know how the number in the formula corresponds to the prefix in the name and go in either direction. So if we have SF4, we need to know that the two elements are sulfur and fluorine. Because there's only one sulfur in the formula, we don't put the mono on the first one. That's the only thing that you have to remember. There's one sulfur, but we don't need a mono there because it's the first element in the formula. So again, just to remind you, no mono prefix on the first atom if there's only one of those in the formula. If there's more than one, it still gets a prefix, but if there's only one of them, it doesn't. But then for fluorines, so 4 is the prefix tetra. F is fluorine, but we do still change the name of the end of the name to IDE. So the F4 part of the formula will be written as tetrafluoride. Tetra telling us that there's 4 of them. IDE just because it's the second element in the name. There's not really a good rhyme or reason for that. That's just how it's done. Okay. Very similar example. P2O5. This time the first element in the formula has more than one of them there. So we need the prefix for that, which is di for 2. O5, the prefix for that is penta. And so we would write this as diphosphorus. I spelled that right, phosphorus, yes. And then again, sometimes for these, this is oxygen, which starts with an O. So often you'll see the A left off. I think you might see it both ways. So I don't want to say that one is like right or wrong, but you often see the A left off. So pentoxide, but it's probably fine. And you might see it in some cases right as pentaoxide. So sometimes there's not as strict of rules as we would like. So you might see it both ways. I think pentoxide is more common, or at least that's the way I was taught many years ago. So diphosphorus pentoxide, but again, the key parts of these are the prefix is di for phosphorus because there's 2 of them, pent for oxygen because there's 5, IDE and name, don't forget that. All right, going from name to formula is even easier because in binary covalent compounds, there's just 2 elements. You put them in the formula in the same order that they're listed, and you just use the prefixes to translate how many of them are in the formula. There's nothing else to it. So this is probably the easiest part of nomenclature, in my opinion, is going from the name to the formula of a covalent compound. So if you just look at the name here, nitrogen trichloride, we have to know the symbol. So I guess that's not necessarily trivial, but will be as you get familiar with it. But nitrogen is N, no prefix, so there's only one of them. That's the first element. Trichloride, so chloride is from chlorine, which is Cl. Tri means 3, so it's just NCl3. Okay. And then disulfur decafluoride. All right, so sulfur is S. Di means there's 2 of them, so it's going to start with S2. Fluoride comes from fluorine, which is F. Deca is the biggest prefix we have in this course, which is 10, so S2F10. And again, we don't reduce that to SF5. It's fine to have covalent compounds that have reducible ratios. So it's S2F10 is exactly where you would stop. Okay. All right. Any questions on binary covalent compounds? All right. The last couple things we're going to talk about, I think this is the last category. Yeah, is acids. I mean, we're going to do more with acids later on. So for now, we just want to be able to sort of recognize them and do a little bit with their naming. It's a little bit different. They're technically covalent compounds. So what an acid is, for our purposes now, is an anion. So either a simple anion from the periodic table, like chloride, fluoride, bromide, or a polyatomic anion, the ones that we just covered earlier today. So it has an anion in the formula, but the cation for that is hydrogen, which is technically a nonmetal, but in acids sort of behaves like H plus, almost like an H plus cation. So it's going to look, the naming and the formulas are going to look kind of like ionic compounds in some sense, but they're going to start with H instead of a metal. So ionic compounds start with a metal, acids start with H in the formula. And so the way that we name them is a little bit different and a little bit takes a little bit of getting used to, I would say. But basically, we have two kinds of acids. So one is a binary acid. We've used the word binary a few times today, and that, as we said, just means two elements in the formula. So a binary acid is just H plus at the start with a monoatomic anion. So the formula is basically, again, just a balanced charges. The anion has a has a charge associated with it that we can predict from the periodic table, and we just need as many hydrogens in the formula to balance that charge. So examples of this would be HF, F minus with H plus. So it's an F minus anion with an H plus as sort of like the cation, even though it's a covalent compound. HCl, HBr, and then sometimes if the anion has more than one charge associated with it, like S2 minus, it would need two hydrogens to balance the charge. So you could have binary ionic compound or binary acids that have two hydrogens or more than two as well. The way that we name these is to indicate that it's a binary acid. It starts with the prefix hydro. Then you have the root name of the anion. So that's whatever element the anion comes from. And then, so this is fairly complicated. There's like three parts to it. Then you change the ending to IC for the anion, and then separate word acid. Okay, so it's hydro, the root name of the anion, which is the element that it comes from. You change the name of that to IC, and then it becomes acid. Okay, so as an example, HCl, binary acid, starts with hydrogen, has a chloride as an anion. So the name starts with hydro. That indicates that it's a binary acid. Cl is chlorine, so the root name is chlor. And then instead of the INE or IDE ending, it becomes IC for an acid. So hydrochloric, separate word, acid. So HCl will be hydrochloric acid, HF hydrofluoric acid, hydrobromic acid, hydrosulfuric acid. Anything that starts with a hydro would be a binary acid. That should immediately clue you in. All right. Yeah, and this is a fairly complicated topic to introduce at this point, so we don't really know what acids are, but we're just getting you familiar with what they look like and how to name them, so that when we cover acids later in the course in chapter 6, you'll have at least that little bit of an introduction to them. And then oxoacids is another common class of acids where you have H plus paired with polyatomic oxoanions. Those are the anions that have a central atom with a bunch of oxygens around them. So examples of these would be if you have HNO3. NO3 is the nitrate anion, one of the oxoanions with nitrogen, with one H plus to balance the charge. Or if you had H2SO4, sulfate, as we talked about earlier, is SO4 2 minus, so with two hydrogens to balance the charge. And then what you basically do for the names of these is the root name of the anion. You change the end of the anion name to either IC or OUS, and then acid. So this would be like if you have an ATE anion, that gives you an IC ending for the acid, or an ITE anion is an OUS ending for the acid. So H2SO4 would be root name is sulfur for sulfate. IC, because it's so sulfate is ATE, so the ending becomes IC and then acid. Or this one would be nitric acid, nitrate, so the ATE becomes an IC. So basically the ending of the name in the acid, whether it's IC or OUS, is determined by the name of the anion. If the anion ends in ACE, the acid name ends in IC. If the anion name ends in ITE, like nitrite, it would become OUS. So HNO2 would be nitrous acid with an OUS after it. Okay, so that's going to be oxoacids. Really, the key to these is to learn the names and the charges of the polyatomic anions, because that's where those are all going to come from. All right, so just one more sort of multiple choice example problem or a couple more to close out this part of the course. All right, so give the molecular formula for hydrofluoric acid. So if you look at the name of an acid, again, look at the very beginning, because that tells you whether it's a binary acid or a more complicated one. So anything that starts with hydro, we would expect it to be a binary acid. Or certainly not an oxoacid. So if it starts with hydro, it's not going to be something like this, because those are going to have oxo anions in them, HFO, HFO3. And then, as we said, there's now only two choices left, HF or FH. The formula of an acid always starts with H. So hydrofluoric acid will be hydrogen with fluoride. So HF is the correct formula, and H comes first when we name acids or give their formulas. All right, so hydrogen first, then the anion. So that's the correct way to do it. So choice A would be the correct answer here as well. Okay. So that's the right formula, but the wrong order. FH would be the right number of each atom, but the wrong order. And then the proper name for H2CrO4. All right, so this is again one of our weirder polyatomic anions. That's why I included it here, just to clue you in on it. So CrO4, two hydrogens, that already tells us that it's 2-, but you'd have to still remember that in other contexts. So CrO4 2- is called the chromate anion. So it's another one of the oxo anions that has a metal at the center. There's a couple of those or 2 or 3 of those that you'll see. All right, but as we said, though, if you have the name of the anion, the name of the acid follows from that fairly straightforwardly. So for oxo acids, you don't need any prefixes. So the hydro, this one's out because there's no hydro prefix in any of those, but you just look at the name of the anion. ATE becomes IC when it turns into an acid. So chromate becomes chromic, and then just the word acid after it. So perchromic is not correct. There's no per in the name of that anion. Chromous would be if it was chromite, which I don't even think exists. That one's wrong, but IC is the correct ending for that. So we go with choice C there. If the anion ends in ATE, the acid takes the IC as its suffix. All right, any questions on nomenclature? That takes us to the end of chapter 3. So I'll put a note here in case this is let me put it at the end of the table. I don't want to confuse you guys. Okay, so that's the last slide. And then, as I said, in case you don't have the textbook or are confused about which tables you should look at, I don't think they've changed. Maybe the numbering has changed, but those are the ones we need. So right here really is the end of exam 1 material. All right. So nomenclature, at least in our lectures, is the last topic for exam 1. Anything we've covered from day 1 until now is fair game for that first exam. Look at Canvas, we do actually give you a little bit of a hint about the content of the exam. If you look in each unit in Canvas, it lists the breakdown of the exam questions. So exam 1 has there's 23 questions, and I think like 16 or 18 of them come from chapters 2 and 3. So the most recent stuff that we cover, the most dense stuff that we cover, is going to be sort of heavily featured on exam 1. But a little bit from a review chapter, a little bit from chapter 1. So don't completely forget about those. All right. So what we're going to move into for the last 20, 25 minutes of today are going to be the beginning of chapter 4. So in chapter 3, we learned about covalent bonding and forming covalent molecules. We just talked about how to name them today. Last lecture that I missed that you're responsible for, we talked about how to draw their sort of two-dimensional Lewis structures that indicate all the bonding and non-bonding electrons. Chapter 4 is a lot more detailed information about covalent bonding, and it starts with how to predict the three-dimensional shape of a covalent molecule. So when you draw Lewis structures that we covered last week, which is going to be one of the chapter 3 topics, a Lewis structure is kind of like, I don't think this children's toy exists anymore, but when I was a kid, there was this children's toy called Flat Folk City. Has anybody heard of that? Clearly not. Okay, so it was just like a set that had like buildings and people, but the people were like flat, they were two-dimensional. And so that's exactly what a Lewis structure. A Lewis structure is like the Flat Folk City molecule. But what we really care about for chemistry, and as we'll see a little bit in this chapter and more if you go into more advanced chemistry courses, is that the shape of the molecule plays a big role in a lot of its key properties. So we have to know the three-dimensional shape of a molecule to make some of those predictions. And so that's the first thing we're going to cover here in chapter 4. And the approach that we use to do it is called VSEPR, sometimes pronounced as VSEPR, even though it's not quite spelled that way. And what it stands for is valence shell, electron pair, repulsion. And the whole idea with VSEPR, it's not even a lot of chemistry. You have to use chemistry to get the Lewis structure correct, because the VSEPR predictions start with the Lewis structure, or at least a reasonably good approximation of it. You don't need to have all the details worked out, but mostly. But VSEPR is basically a geometric approach. It's not really a chemistry-based approach. It's saying that we have a central atom, you have a bunch of things bonded to it, maybe a lone pair or two in the central atom. All those bonds to the central atom and all the lone pairs are made up of electrons. Electrons repel each other, so we're just going to try to put the electron pairs as far away from each other as we can. So however many electron pairs you have around the central atom, let's arrange them in the way so that they're totally as far away from each other as possible, not clashing with each other, not repelling each other. So it's really just a geometric approach to figure out how to do that. So you're just going to place electron pairs that I'll say electron pairs because that's how it's really done, is each pair of electron counts as one group. So we place electron pairs around the central atom. As far away from each other as possible. All right, so that requires us to have a Lewis structure that indicates how many electron pairs there are around the central atom. And once we know how many there are, we just try to arrange them so they're as far away from each other as can be. And it's just a geometric argument, really. So within this, there's going to be sort of two ways of then describing the shape that results from that. So one is called the electron group arrangement. These two are related to each other. Basically, electron group arrangement is a category, and then molecular shape would be a subcategory within that. So the electron group arrangement is the three-dimensional geometric shape that all of the electrons, the bonding and non-bonding electrons, occupy. Right, so again, we're talking about primarily molecules here that have a well-defined central atom, and they're bonded to a bunch of things on the outside of that central atom that surround it. But sometimes there's also going to be lone pairs in the central atom. So when we cover Lewis structures, or when you went through that last week, you remember that sometimes the central atom has one, two, or possibly even as many as three lone pairs around it. They're non-bonding. So the electron group arrangement takes all of those electron groups, the ones that are involved in bonds to the outer atoms and ones that are lone pairs, and that's going to be the shape they occupy. The molecular shape is going to be the three-dimensional shape that only the atoms occupy. So the lone pairs are still there, and they influence what this shape will be, but the molecular shape just describes the shape that the bonded atoms occupy, which is kind of like what the molecule looks like. You can almost think of it as the electrons are there, but they're invisible. what we really can see in chemistry, now that we can actually see it, but as an analogy, what we really see are the atoms that are in that molecule. And so the molecular shape describes that. So as we'll see when we move forward with this, if you have 0 lone pairs on the central atom, if everything around the central atom is bonded to it, then the electron group arrangement and molecular shape are the same. But if there's 1 or more lone pairs, when we're describing the molecular shape, we ignore the lone pairs and just describe the shape that the rest of the atoms themselves are occupying. Right. So the way we're going to do this is we're going to sort of systematize things in this way. And I don't think your book does it exactly this way, but I do really like this approach, which is to use what's called the AXE notation to categorize the different possible three-dimensional structures we can have. And so basically what you have here is A is just the central atom. You don't really even need that in there, I suppose, but that's the central atom in the formula. X is an atom that's bonded to the central atom. And then E in this notation is a lone pair. And then these subscripts M and N are how many of each of those you have. Again, keep in mind that E is an entire pair of electrons. That's how many pairs of electrons you have, not how many total electrons you have as lone pairs. That's how many of each you have. And so that combination of M and N are going to dictate what the molecular geometry is. The total number, M plus N, will give us the electron group arrangement, as we'll see, but then the combination of M and N you have defines what the actual shape would be. So in this notation, the X, which is an atom that's bonded to the central atom, and E, which is a lone pair, these are referred to as electron groups. All right. Now, another term that doesn't seem to be used much anymore, but I think is helpful, is what's called the steric number. And basically, this is the sum of the two subscripts M and N. It's the total number of electron groups that are around the central atom. That number is important because it defines the electron group arrangement. As we said, there's sort of two things we're going to talk about. The electron group arrangement, which is the arrangement of all of those, and that's going to be determined by the steric number. Total number of electron groups, I should say. Oh man, I'm messing up here. That should be, let's put it there. The total number of electron groups, make that grammatically correct. One nice thing about the VSEPR approach, when we introduced Lewis structures, we spent some time discussing how to determine what the bond order is. Are these two atoms bonded by a single bond, a double bond, a triple bond? We had to satisfy the octet rule, minimize formal charges. There's a whole laundry list of things we had to do there. The nice thing is for VSEPR, we don't really care whether it's singly bonded, doubly bonded, or triply bonded. If an atom is bonded to the central atom, it counts as one electron group, whatever the bond order would be. So the bond order between A and X doesn't matter for this method. We might talk a little bit in the future about some subtle effects that the bond order has, but for just categorizing the shape in this way, we don't need to know whether it's singly bonded, doubly bonded, or not. So X always will just count as one electron group, no matter what the bond order is. So what that means then is for this AXE notation, the number of X's just comes from the formula of the compound. So if I give you the compound SO3 and ask you to, do VSEPR on that, well, you already know that there's 3 X's in the formula because there's 3 oxygens. You don't have to look any deeper than that to get that number there. The part that requires the Lewis structure is to figure out how many lone pairs should be on the central atom. That's the part where you have to at least get most of the way through the Lewis structure to get that, and that's critical as well. So you can't just take too big of a shortcut, but at least to get this first part, the number of X's, that just comes from the formula of the compound itself. And then another important term is the bond angle, which we're going to classify these structures in terms of. This is the angle between two bonded atoms with the central atom as the vertex. So as an example, one thing that VSEPR will allow us to do is predict that water, H2O, has a bent shape. It's not linear with the two hydrogen atoms sticking out straight to the side. It actually is more of a bent V-shaped type thing, and VSEPR allows us to predict that. But one thing we can categorize in any of these structures is the angle between two atoms there. So that would be called the HOH bond angle, where, again, the center atom at the middle and then two atoms bonded to it, what angle do those make up? That's going to be useful for sort of understanding these structures a little bit and characterizing things about them. So the approach we're going to take then is we're going to go through one by one all the different possibilities of different numbers of total electron groups, different combinations of atoms and lone pairs, and just see what the structures look like. And it doesn't get too big. The most number of electron groups we'll have is 6. So we're going to go 1 through 6. It's not too many combinations, but within each of those, often there's different combinations of M and N that we have to be familiar with that give us slightly different shapes as well. Now, what I have linked here is a simulator that I think is amazing. So I'm going to actually going to flip back and forth to that today to show you how it works. It's a lot better for visualizing the structures than me trying to draw them. You should know how to draw these, but this simulator is really good here. So we're going to start with 2 electron groups. One electron group, hopefully you understand, is trivial. That's just 2 atoms bonded together. They have to be linear. There's no other way about it. But with 2 electron groups, they could be linear, or as I said, they could be bent. Now, as we've said, VSEPR, the whole idea here is to put the electron groups as far away from each other as possible. So if you have 2 electron groups, 2 atoms bonded to the center atom, then they should be 180 degrees apart to get as far away from each other as possible. So the simulator will show that. So let me go to that real quick. Hopefully this comes through okay on the recording, but as you can see, if we have 2 electron groups here, we can rotate the structures as well. And they end up, the 2 bonded atoms end up 180 degrees apart from each other linear. That's the farthest away they can be if there's 2 of them. All right, so when we have AX2 with no lone pairs in the center atom, just going to slow down my tablet. Let me save this before it crashes. All right, it's getting slow here. Probably going to die here in a second. All right, but this one's going to be linear for both the electron group arrangement, because there's only two atoms, and for the geometry. So when we have no lone pairs in the center atom, the electron group arrangement and the geometry are the same. Okay, so that's going to be a linear for both, and the bond angle in this case would be 180 degrees. I really want to use that simulator, but it seems like it might be slowing things down, so I might have to close this and see if that gets better. Yeah, it is. Okay. All right, that simulator is going to bog us down too much. So I definitely encourage you to go through it, though. I might pull it back up if there's any confusing ones, but the ones we're doing today are mostly 2-dimensional, so it shouldn't be too hard. I might get back to it a little bit. Okay, so then if we have AXE, again, this one's fairly obvious because there's just 2 atoms bonded to each other, so they have to be linear. But in AXE, there's still a total of 2 electron groups, 1 atom, 1 lone pair. So so both of them are going to arrange 180 degrees from each other, but one of those is a lone pair in this case. So it would still be linear, and there's not going to be a bond angle because there's only 2 atoms. You need 3 atoms to have a bond angle. So bond angle not applicable in this case. And so just as again, a little reminder, all diatomic molecules, if there's only 2 atoms in the formula, whether it's 2 of the same or 2 different, all diatomic molecules have to be linear. Just from a geometric standpoint, that's the only way they could do it. So you don't have to do any predictions for those. H2, Cl2, CO, anything that has just 2 atoms in the formula, you're going to get those 2 just linear. That's the only way about it. So 2 electron groups is pretty straightforward. Now, when we go to 3, things are a little bit different, but still 2-dimensional, so it's not too bad for us. So with 3 electron groups, if we have no lone pairs in the center atom, that's going to be the first case we consider, which would be AX3. For AX3, what we have now 3 electron groups around the center atom. We want them as far away from each other as possible. And the way you do that is with an equilateral triangle. 120-degree angles between each of them. So that's going to look like this. This one's easy enough even for me to draw with my limited artistic abilities. So it's just a triangle with the 3 atoms, totally flat. So what we call that is trigonal planar. The planar telling us that it's flat. And again, we're going around 360 degrees with 3 different angles that are equal. So the bond angles are each going to be 120 degrees. All right. But then with 3 electron groups, it is also possible. This is not a very common arrangement, but you can have situations where you have 2 electron groups bonded to the center atom, 2 atoms bonded to it, as well as 1 lone pair. So you need to draw the Lewis structure, at least get most of the way through it to predict that you would have a central atom with 2 bonds and a lone pair. Now, when we're placing lone pairs in VSEPR, it turns out that the lone pairs, they repel more strongly than bonding pairs. Bonding pairs are constricted between the 2 atoms. Lone pairs kind of spread out a little bit. So they repel more strongly. So we want the lone pairs to be as far away as possible. Those kind of take precedence. For most of the structures, all of the positions are identical. So for this trigonal planar structure, it doesn't matter whether we put the lone pair in any of those 3. They're all the same. They're all 120 degrees apart from each other. So I'll put the lone pair up there just to make it easier to visualize the geometry. And so then in this case, what you would get are the 3 atoms are bent relative to each other. Not linear in this case like we had for AX2, but bent because of the lone pair there pushing those 2 away. So we call this the bent geometry, or sometimes you'll see it listed as V-shaped. And the bond angles in this case, this is where the first time we have to talk about the influence of lone pairs. These lone pairs, as I said, push a little bit stronger than the bonding pairs. So what they're going to do is they're going to push down on these bonds here a little bit harder than the bonds push back, and that's going to compress the bond angles a little bit. We can't predict how much. It depends on the identity of A and X and all that stuff. There's no easy way to predict it, but the bond angles will be a little bit less than 120. Still close to it, so you're thinking like maybe like 117, 116, not like way far off from it. But because of the lone pair there, it's going to press down on those bonds a little bit, and you'll see that decrease. All right, for the last ones we're going to cover today are 4 electron groups. For this one, I want to try to bring the simulator back up and hope it doesn't crash our system. It's probably time for a new tablet is what this is telling me. So let me get the simulator back up eventually. Of course, Firefox is updating now. Maybe that's why it was slow before. Let's see. All right. All right, so this is back here in what I had pulled up earlier. So if we want to do 4 electron groups, the way you do that is you just click or tap these atoms up here to add them on. So we're going to do, this is 2, we have 2 more. All right, so the shape here is, now we're in 3 dimensions for the first time. And it's called tetrahedral. You can almost think of it as kind of like a 3-legged stool with one sticking up the top like that. So it's good to sort of do this on your own a little bit to sort of get used to what these shapes look like. But essentially, and they call it tetrahedron because basically if you were to draw if you were to use these atoms as the corner, there would be 4 sides in that shape. So that's why it's called tetrahedral, but also means that there's 4 electron groups, which is helpful. All right, so you have this sort of shape here. It's like a 3-legged stool with one sticking up from it. And see if I'm slow again. So for the way that we would draw this then, yep, it's going to slow me down again. I have to close it every time. This is annoying. I blame Teams because Teams takes up like way too much of a computer's memory. All right. So with AX4, the way we do it is we have 2 atoms that are in the same plane like that. And then the other 2 are sort of perpendicular to that. So you would have basically 2 groups of atoms, one that are, 2 that are in the plane, then 2 that are rotated to that. So the way we draw those is with a little wedge that indicates that that one is coming out towards you, and a little dashed wedge to indicate that that one's going away from you. But again, this is now a 3-dimensional structure where you can think of it as 3 atoms at the base that make up sort of like a 3-legged stool, and then one above it at the top there. So we call it tetrahedral. For you guys, mostly it's going to be just knowing the names. It's helpful to visualize things, in my opinion. But and the bond angle for this is totally unintuitive, so you just have to remember it. 109.5 degrees. I guess if you're really good at three-dimensional geometry, you could have predicted that, but most of us aren't. So 109.5 is the bond angle for tetrahedral. So then if we wanted to put, and here's a little picture that shows why we call it tetrahedral. If you draw sides through all of those corners, you get 4 triangles around that. So the central atom here will be right in the middle of that. Okay, so that's what tetrahedral looks like. If we do AX3E, so there's a total of 4 electron groups, 3 X's, 1 lone pair. So the total is still 4. So those 4 things have to still be tetrahedral. The number of electron groups defines the arrangement of all of them. Anytime there's 4 total, they're going to be tetrahedral. So the basic shape's going to look like this. And then where do we put the lone pair? Once again, for tetrahedral, all the positions are identical. So they're 109.5 degrees apart from each other. So we can put the lone pair wherever we want. I like to put it at the top again because that helps us visualize the rest of the shape a little bit easier. So the 3 X's go down there. And what we call this is trigonal pyramidal. In trigonal planar, the 3 X atoms are in the same plane. They make a triangle. And trigonal pyramidal, again, they kind of like make a 3-legged stool. This time there's nothing above the stool. It's just the central atoms at the top. So it's kind of like a pyramid shape, and that's what we call it, trigonal pyramidal. And the bond angles are still going to be not that different from tetrahedral, but a little bit smaller because of the lone pair, again, pushing down and everything. So they're going to be a little bit smaller than 109.5. As an example, ammonia NH3 has this shape here that I'm showing, NH3. And the bond angles in NH3, I believe, are about 107. So they're like 2 degrees smaller. It's not a huge difference. All right, let's try to finish this off. And then the last possibility with 4 electron groups is AX2E2. Still 4 total electron groups. 2 plus 2 is 4. So we have to start with the tetrahedral arrangement. And it still doesn't matter where those 2 go. They can be any of the 2 positions because they're all 109.5 degrees apart from each other. They're all identical. So we can put the 2 lone pairs there, for example, and the 2 X's. This doesn't as easily show the geometry, but if we rotate it into the plane, what we can draw it as is like this. So you have the A and the 2 X's, and then 1 lone pair coming out towards you, 1 lone pair going away from you. But the key thing for the molecular geometry, the electron group arrangement is still tetrahedral, but the molecular geometry is just defined as the shape of the 3 atoms, which is going to also be bent or V-shaped. So one pattern we're starting to see is that if you have 3 atoms in the formula, AX2, whatever A is, whatever the 2 X's are, the only 2 possibilities are bent or linear. AX2 was linear, AX2E was bent, AX2E2 is also bent. The difference between those 2 is the bond angles are even smaller for this one. So in this one, the bond angles come from tetrahedral, so they're going to be around 109.5, but again, a little bit smaller because of the lone pairs. So water is an example of AX2E2. Water has bond angle of about 105 degrees, if I remember correctly. So it's even a little bit smaller because now there's 2 lone pairs pushing down, but it's smaller than 109.5. So 2 different bent geometries that we saw, AX2E, AX2E2. AX2E is close to 120 degrees. This one's going to be a little bit smaller, closer to 109.5, but both have the same name, bent or V-shaped. All right, we'll get through 5 and 6 electron groups next time and move on to some things that we can predict once we know the geometry.